So in this demo, we're going to look at the similar processes we did before with creating a triangle and rendering it. In this case, you can see I've also got it animated just to demonstrate some other principles. Now, this is the WebGPU version, and WebGPU works in a very different way to OpenGL. In particular, all the rendering happens across a buffer, in this case a NumPy buffer, which we are then blitting to the screen to look at our final result here. So let's start with that part, because what I've done is I've written a class here called NumPy buffer widget. The idea of this is that it's an abstract class that any user that wants to render a NumPy array to the screen can use, and it's been implemented in a similar way to how the OpenGL widget in PySide works as well. So what we've got here is basically a meta class. So we're importing from ABC Meta an abstract method. These are the methods that the user are going to have to implement themselves to use this. So basically the NumPy buffer widget is implemented as a queue widget, which means it will pick up signals and slots and everything else. It also has a few other features in there to allow us to simply render text. We have a flag initialized, which is defaulted to false. We have a text buffer, again is an empty list. This is internally going to store positions, strings and colors and sizes. We have the buffer. This is the NumPy array that we're going to use to render to the screen. And then we've got a few other elements in here. So we've got an update timer that is triggered so that basically we can update and render every time things happen here. So what we do is we have the timer here, it's a queue timer. We then connect the timeout of this timer to update, and that will just keep doing the timer there. And basically we go through now. The user has to implement initialize buffer, paint. Under the hood, paint will eventually implement the paint event here. So the paint event is a Qt paint event. So when update is called and Qt calls the paint event, that will go off, and then if the buffer is not initialized, it will initialize it and set things up. So this is the equivalent to how initialized GL works under the hood for the QOpenGL widget. And then we call our own paint method. Then we also then go through, if we have a buffer allocated, we'll call this present image, which I'll look at. What this will basically do is to take the NumPy buffer, convert it into a queue image and display it on the screen. After that, we'll go through and we'll render our text on top of the canvas that we've got here, and then finish. So render text basically goes through. This is called by the user. It passes in X, Y, the text string, the size of the font to use, and everything else. That gets stored and appended as a simple entry here into our text buffer, and then later on that goes through and it uses that information to draw text. So we're just using all the built-in Qt stuff to do that for ease. We could, if we wish, implement our own rendering algorithms under the hood using OpenGL, for example, or WebGPU, but for now this was the easiest approach. I have a resize event. Again, that's just going to call the parent resize event. And this is the core. This is the present image. What this does is it takes the NumPy array, it gets the height and the width from the shape, then it converts this into a queue image. Queue image handles sort of lots of the underlying conversion and other stuff. For this, basically, we are going to store our data into RGB 88888, and then depending whether we want to flip it or not, we can flip it. and then this is the bit that just basically grabs the rectangle that we want to render to and copies one to the other. So nice, simple, easy sort of method to use. I use this in all my demos. This will work in Vulkan as well, and so we use it in Vulkan. Still minimal working process. There's a few things that I might change, but for the most part this has been working quite well for a lot of demos that I've been using. Now what we've got here is a application now to use that widget and initialize WebGPU to build our program. So unlike the previous example where we had to set up the OpenGL context and everything else, in here we don't, because we're doing that all as part of the initialization of our program here. So we're literally constructing this WebGPU scene and then going off and doing stuff. Now the underlying core of this is here. So when we initialize, we need to go through and initialize our NumPy buffer widget. So that's what we're calling here, setting our title here. Now, WebGPU itself has a device, a pipeline, and then we're going to create a buffer of data that we are going to use when we're rendering and everything else. And in this case, I've got some other attributes, so angle for the rotation. This is my vertex data as we used in the previous one. It's just a NumPy array. And this is the size of our buffer that we're rendering to. So this is our render target. Now this must be in powers of 2. So if we start modifying this, you can see here that's in a power of 2 by power of 2. That's happy. So we've got more dimensions on width and height here. If I were to make that something along these lines here, it's still working. So generally what we'll do though is make this a square buffer. So for example, we can make this 128 by 128. What this basically is now is the render target. This is what we're rendering to. So you can see here it's very, very low res. We can go down lower. So what happens is WebGPU will render to this buffer, and that buffer is then blitted to the screen to generate what we do. So the bigger this buffer is, the more pixels we've got, the better the sort of resolution. So we can do, 1024 times 4, 1024 times 4. We've got a bigger buffer now. So you can see we've got smoother, better looking, still get jaggies because the nature of how computer graphics works. So that's a bigger buffer there. For most of these demos, I'm just using a 1K buffer for simplicity. These need to be integer values, and as I say, they need to be powers of 2. So if I do 1023, for example, like that, you can see here, bytes per row must be a multiple of 256. So we've got to be wary when we're doing this. Otherwise, it won't work. So this is the render target. So what we need to do when we start, we need to initialize our buffers. So this is going to be called when we're ready to get going. And in this case, first thing we do is from the WebGPU library, we ask for the default device. That's going to grab our GPU for us. If we can't get that, then throw an error because we can't do anything else. After that, we're going to initialize our buffers. So this is the data I want to use for rendering. Then we're going to basically create a render pipeline. What that says is, this is how my data is formatted. This is the shader to use. Here are the buffers that you render to, and this is the processes you use each time you render a frame. And this gets quite complex. We'll explain more of this in depth in the lectures. So first thing I'm going to do, create an empty buffer. What you can see here, this is our buffer which has MP0, so an empty buffer with 4 components, RGBA basically, and it's an unsigned integer 8. So this buffer is the buffer we're going to use for rendering on our paint event. So first thing we do is initialize buffers. So we create a vertex buffer. A vertex buffer is a special buffer that is used to hold vertex information. So in our case, it's going to be an XYZ and an RGB. And you can see here, this is specified as size, self.vertices.n bytes. So it's specified in bytes. And we give a usage hint again. So the usage is a vertex buffer and it's going to be copied to destination. Again, we'll explain more of these in depth when we get to them in lectures. Next, we're going to create a temporary staging buffer for updating the vertex buffer from the CPU, and this makes it mappable so we can do various things with it. So this is our copy buffer here. So vertex buffer.copy buffer is create a buffer, again the same size. This is map to be written, and this is copy the source, so we can copy to us. So we've created our buffers there now. That data is ready to be made available to the GPU. Next, we need to create our render pipeline. And this is where things are per project, per data, per shader dependent. And this is where the bulk of our work in modern graphics APIs like WebGPU and Vulkan come into play. In OpenGL, it's pretty much set and we do things in a certain way. Here we have maximum flexibility. Now, I'm not going to go too much into the WebGPU shading language in this one, but basically similar, we have a vertex in structure. So location 0 is position, location 1 is color. I have a vertex out, which has a position, which is, as you can see there, a built-in type. So it's a bit like GL underscore position, and an output, which is a frag color. Then my vertex shader, again, has an input and an output. And in this case, the output is just going to be the position and the fragment color. Sorry, that's the vertex shader there. So what I'm doing is I'm outputting the position and I'm outputting the fragment color, and then my fragment shader here reads that value in and just returns that to say this is the color of the pixel. Next, we're going to create a pipeline. So the pipeline is basically how we render things. So in this case, we're creating our pipeline based on a default layout. So in this case, we're saying, so bind groups will come across in later examples, but we're generating a default layout. We're then assigning that as the layout of this pipeline. We're not binding anything in this case, it's just empty. Then we're saying this is how the vertex data is set up. So here is the vertex shader code. So that's the code that I generated earlier on. We're creating a shader module from that code, and main is the entry point. So that's the name of the function to call. Then we have to say how our data is laid out. So in this case, it's an array stride of 6 by 4. So 6 values, which is the XYZ RGB, multiplied by 4, because that's 4 floats. Ideally, I should use an MP type here. I will modify that a bit later. And then we say this is vertex data, and then we say the format. So this is the equivalent in OpenGL of the vertex attributes. So we're saying it's float 32 by 3, so that's the equivalent of a vec3. The offset into the data stream is 0, and the location in the shader is 0. And then in the next one, you can see same sort of thing, but now it's 12 bytes in, and the location is 1. When we get to more complex data structures, I'm using NumPy to explicitly get these values, as we'll see in later examples. The fragment shader, the fragment part of the pipeline is creating the shader from here. Again, main is the entry point. This has a target now, so this says what to render to, and we have to specify the format. So this is red, green, blue, alpha, 8 bits per channel, unsigned, normalized. And the topology is what format is this data? In this case, it's a list of triangles. And again, this is where it differs from OpenGL. OpenGL, you normally just explicitly specify when you draw the type. Here, we must do it as part of the pipeline, which makes mixing pipelines a lot more complex. So we're ready now. So when we need to render now, what we need to do is we need a texture to render to. So here's our texture view. This is our texture that we are going to render to. So we're creating a texture. In this case, it's width by height by 1. It is a format of RGBA norm. It's a render attachment, so it's for copying data to. And then we're creating a view to that so that we can reuse it. Next, we need to create a command encoder. The command encoder basically says what we do when we want to render. So we basically say what data is attached, how we're going to use that, and how we're going to generate different things. So in this case, we're beginning our render pass, and we're saying there's a color attachment here, which is the texture view that we've just created. When it's loaded, clear it with this clear value, so that's the background color effectively. And then when we write to it, store that value. Now there are other things here, and we'll look at different examples as we go through more complex pipelines and things like that. So now, in my render pass, I'm saying use the pipeline we created earlier, allocate the vertex buffer, so that's the vertex buffer we created earlier on. Finally, we're saying draw that value, and that's drawing 3 vertices in this case, so the 3 in the NumPy array. And then we're ending our render pass. Now, at the moment, that's just sitting there as a pass object. I'm creating it every frame. Typically, we might not do so. It depends on the context, but in the case of this, I've done it for simplicity. Next, we're going to submit that to the render queue, which will basically line it up to be rendered. Once that's finished, we can grab the result of that render and do our work. So this is the update color buffer. What this does is it grabs the buffer size, so width by height by 4. We then say, I want to map this buffer. So I want to create a buffer here for reading my data back. We then create a new queue. And this is basically saying, this is the source data. So this is where I want to read from, which is my texture buffer previously. This is where you're going to write to, the readback buffer I've just created. And this is how the data is formatted and how much to copy. We then enqueue that. That will copy the data back. We have to map this to make it CPU accessible for reading. Read that data back. Convert it to a NumPy array. So this is converting that to a NumPy array. And then that's assigning it to self.buffer, which is the one that's going to be rendered in the other widget as we go through. And then we unmap the buffer when we're finished. Timer event, very simple. I'm just updating my matrix here and rotating them, going through here. So we've got our different values there. The only difference now is what I'm doing with this temp buffer that I've created each frame. I'm now copying that back to my vertex buffer data. So every frame here, I'm creating a new command queue. So command encoder, I'm copying that buffer, and then once I've finished, I submit that queue. So what that's going to do is dynamically update every frame, the buffer, which is then being updated when we call the render. So every frame, that's being called, that's updating the initial buffer, and then that's being used in the render. So there's synchronization going on between all of these queues just because of the way that I've set it up. Obviously, we can do far more complex setups and things like that. As we go through more examples, we'll modify slightly how we do these things for a bit more efficiency, but this is done for ease this time. Key press events, obviously, is just to escape now because all of the OpenGL type wireframe drawing commands don't exist anymore. If we wanted to draw wireframe, we have to go and modify our pipeline and tell it that this is a line list. And then when we run that, you can see that's working there. Sorry, I need a line loop, I believe. Nope. Was it lines? No, I can't remember the topology now. I'll have to remember that. There is triangle list, obviously, like that. There is point list. You can sort of just make out those points are a bit too small and so on. But again, we'll go through lots more of these at a later date.